This is a brief introduction to the KEEL Dynamic Graphical Language. Unlike most computer languages that are scripted to process information using if-then-else logic, the KEEL Dynamic Graphical Language focuses on an information fusion process where information is processed collectively. We are focusing specifically on how information is valued to make decisions and how to control actions, and how those valued pieces of information are combined to influence other pieces of information in a web of interrelationships. This is how humans balance alternatives and apply their judgment. Humans use judgment and reasoning to solve problems and control their behavior all the time. With KEEL, we are enabling the capture of this information interpretation process in a manner that can be deployed in today's digital microcontrollers and computers. I will start by opening the KEEL toolkit and starting a new project. A blank canvas is displayed. First, I am adding a new position to the canvas. A position is an output or information fusion point in KEEL syntax. It has a default name of Action 1. Now I am adding a supporting argument. Supporting and objecting arguments are inputs to the system. As soon as these elements are added to the screen, they are active elements. I can stimulate the inputs and observe the accumulated support in the blue bar within the position bar above it. In just a few seconds, I can start interacting with the design. In this introduction, I am just introducing some of the concepts, so I'm using the default names that are auto-assigned. If I was building a real system, I would appropriately label the inputs and the outputs. Now I'm going to add another position. This time I will assign it an importance level of 50. Since the height of the bar is an indication of its importance, it is easy to see that Action 1 is more important than Action 2. Next, I am going to drag a wire from what we call the modified value of Action 1 and use it to control the importance of Action 2. Building a model where the importance of information changes based on a changing environment is something that we encounter all the time in a complex world. You can see that as soon as the wire is connected, the entire system is active. We are building an active KEEL engine behind the scenes without writing conventional code. It is processing all of the inputs, all of the time, integrating information sources as if it was an analog computer. The KEEL toolkit is also making sure that a stable system is being developed. By this we mean that it is one that does not have any circular references, like A controls B, B controls C, and C controls A. If you attempt to create a circular reference, you will get a warning message. Now I will add several supporting inputs to Action 2. I can stimulate them and observe they are active elements as soon as they are dropped on the screen. The KEEL toolkit provides graphing capabilities, so anytime you want, you can graph your relationships and get some additional feedback into your design. Most KEEL designs are targeting complex problems that may not have had well-defined solutions in the past. So the designer is interacting with the design during the development process and observing how the system responds. The designer is making corrections or adjustments until it behaves the way he or she wants it to behave. Development is an iterative process. Now I am going to delete the wire for a moment by double-clicking on a connection point. Since it is so easy to add and delete these wires that define the functional relationships, this kind of interaction is common. This time, I'm going to wire the modified value of Action 1 to the 3 supporting inputs of Action 2. With these wires, we can say that Action 1 is contributing to the resolution of Action 2. So before we had Action 1 controlling the importance of Action 2, now we have Action 1 contributing to the resolution of Action 2. As you can see, as soon as these wires are added to the screen, the entire system is active. And I can add the wire from the modified value of Action 1 to the importance of Action 2 that I had before. Again, the entire system is expanded and active. With KEEL, the focus is on the designer continually expanding the model and getting immediate feedback. If I graph the system at this point, you can see that my model has evolved to a new nonlinear system with just a few seconds of additional work. I can quickly delete the wires from the modified value of Action 1 to the supporting arguments to Action 2 by double-clicking on the blue diamonds below the arguments. And I can quickly change the type of an argument with an edit function, or just by hitting a key to open the Edit Argument window. Again, as soon as the edit is made, the change is made to the underlying KEEL engine. The reason we can change the system so fast and easily is that there is no change to the underlying KEEL engine code. The code is always the same, no matter how large and complex the design grows to be. The problem definition, what we are designing, has all information stored in tables. So the tables change, but the code stays the same. This is a key difference between conventional programming, where as you add more functionality, the number of lines of code expands, all of which must be debugged and maintained. This is not the case with KEEL. KEEL provides a new form of information storage and processing. Now I am adding two more positions to the screen, Action 3 and Action 4. To Action 3, I will add a bias input that is the same as a supporting input locked at 100 and an objecting argument. Then I will tie the modified value of Action 2 to the new objecting argument. So we can say that the resolution of Action 2 is contributing to the resolution of Action 3. Now I am going to drag a wire from the modified value of Action 1 to the triangular icon on Action 3. This icon represents a threshold. Thresholds are used to trigger events, or to turn things on or off. I could set the threshold manually, but in this case I want to demonstrate where the control of an event can be dynamic. To use a threshold, it needs to be tied to something. So in this case, I want to use it to control Action 4. So I will add a bias and an objecting argument to Action 4 and wire the threshold of Action 3 to that new objecting argument. Now, before we complete this brief introduction, I want to add two more supporting arguments and three objecting arguments to Action 1. As I have stated before, all information in the entire system is processed collectively, together. Fundamental to how KEEL processes information is how supporting and objecting arguments, that also might be called driving and blocking inputs, are integrated for each position, or information fusion point. So to show this, I will start by setting all inputs to 0. First, we have Action 1 with a potential value of 100. KEEL engines work with normalized values, so think of a position with an importance of 0 as having no potential importance, and one with an importance of 100 as having maximum importance. With no inputs driving or blocking, the resolution of Action 1 is 0. Think of this as a situation where there are no reasons to do something and no reasons not to do something. Therefore, the accumulation of these reasons is not to do anything. Now we add a 50% supporting argument to Action 1. Order doesn't mean anything since all information is processed collectively. Since this is the only input contributing information to the resolution of Action 1, we have a 50% accumulation. This is shown by a blue bar within the position. The numeric value is shown below. Adding another 50% reason supporting Action 1 increases the support for Action 1 to 75. Adding a third 50% supporting input increases the accumulation of justification to 87.5. Adding a 50% blocking reason reduces the accumulation by half. Another 50% blocking reason reduces it again by half. Now taking the last objecting input, I am setting it to 100. This totally blocks the accumulated justification for Action 1. This KEEL methodology for accumulating information is not averaging the inputs, it is accumulating them. This process accumulates supporting information first and then reduces the accumulated support with blocking information. This means no overrides yes. In industrial automation system, there is a concept called an emergency stop. Normally, this is accomplished by breaking an electrical signal. This is done for safety-critical systems, where you always must know how to stop the system. With this model built into the KEEL information processing system, no will always override must. So if we move one or more of our supporting inputs to 100, any one objecting input or blocking input set to 100 will stop the system. Finally, one of the benefits of a KEEL design is the ability to reverse engineer decisions or actions. This is accomplished by tracing wires from the decision or action back to the source. With just a few hours of KEEL training, tracing KEEL logic will become second nature. When you click on a connection point, wires to and from that point turn red. With a little experience, you will learn which connection points are source points, where information comes from, and which ones are sink points, or those that receive information. With this brief introduction to the KEEL Dynamic Graphical Language, you should understand what we mean by a dynamic language. There are some other computer programming languages that are called dynamic languages, but in these cases, this commonly means that the variables are dynamically typed. We call the KEEL language dynamic because it moves. The KEEL toolkit is also dynamic because it also allows external signals to be read into the development environment during the development process, so changing information can be used during the development cycle when focusing on what-if policy development scenarios. The KEEL toolkit also supports language animation, where you can watch the system think. This is helpful in reverse engineering decisions and actions. This will be more important where there is a need to audit the behavior of these systems. In this introduction, I have only shown some of the functional relationships between information items that are available. The entire methodology for creating KEEL-based models can be explained in 93 minutes of online training to licensed users. The users are taught to think in curves, or to think how information influences decisions or actions. It is simply a matter of wiring the desired functionality together. When the designs have been tested in the KEEL toolkit, they can be translated to conventional code, where the problem is saved as a text file, including one- or two-dimensional arrays of integers and floating point numbers, and a common code set, in one of many targeted programming languages of choice. Pseudocode describing how to integrate the KEEL engine into the user system is included in the text file. Copy and paste the code into your development environment and call the KEEL engine, and you are ready to go. This completes the brief introduction to the KEEL Dynamic Graphical Language. If you have any questions, contact us at CompSim. There are numerous papers and interactive demonstrations on CompSim's website. The interactive demonstrations show KEEL adaptive cognitive engines at work.